Hello and welcome to this short video on Polya's principles. It's by um, it's based on a book by Polya called How to Solve It. Polya was a Hungarian mathematician who initially worked in ETH Zurich and then later moved on to Stanford during the World Wars. And in 1945, he came up with this very famous book called as How to Solve It, which is a set of very simple tools and methodologies which can be used for solving mainly mathematical and engineering problems. So the steps are four major steps: understanding the problem, devising a plan, carrying out the plan, and looking back. So by the steps are seems to be quite obvious. There's nothing very great about it. But what Polya did is just not just classify this as steps, but also come up with what we mean by understanding and how to devise a plan and carry out. So that's what we'll be seeing in this video. So what do we mean by understanding the problem? By understanding the problems, we have, let's say we have a statement of the problem. Now, do you understand all the technical words that are there? Do you understand in what context a particular word has been used? Does it have, usually in technical literature, a particular word has got very specific meaning and not a vague meaning as you would use in literature or multiple meanings that come up in literature. Can you restate the problem in your own words? Right. So, given the problem, understanding essentially means you have grabbed the important concepts in as the problem is stated and just rephrase the entire problem in your own words. Can you do that? Then the obvious thing: what are the knowns, what are the unknowns, and what are the conditions or environment that is likely to, that is specified. Whether it affects or not, we don't know, but whatever is given as environment conditions listed down. Then another important aspect of solving a problem, particularly one in engineering, is understanding a problem, is drawing a picture. So it's very important that you draw a picture of uh, what is happening as described in the statement. Usually, with respect to engineering problems, there is, at least chemical engineering problems, usually it's got to do with some transport of heat, mass, and momentum. There are some reactions, and there could be some physical stresses and so on. But typically, it is with respect to transport related things. So, usually, for all problems in chemical engineering, you will have a very easily describable picture of the problem. So once you draw a picture, it's important that you introduce notations. So you can use notations which are typically used in that particular area or field, and something like axis, direction of axis, and so on. Then you really don't know whether you can solve, but you can take a guess. Is sometimes you, while solving a lot of problems, you get an intuition of sufficiency of information. Do you have all the information? You really don't know at this stage, but you'll know only later. But you might be able to take a guess whether the information is sufficient. Secondly, devising a plan. So what do we mean by devising a plan? So once we have got the list of knowns and unknowns, you just probably either picture it in your mind or put it on a paper in terms of a network diagram like this of connected things. Let's say these are the unknowns, these are the knowns, and this is the unknown. So we want to see how this knowns are connected to unknowns. So this is, let's say this is the big problem. So before solving the big problem, we can solve for a smaller problem. So from these knowns, I can find some intermediate thing. And from that, and another intermediate thing that came from here, I can find this. So this getting this connectivity of knowns and unknowns and intermediate things is one way to devise a plan. So once you have got this, some of the methodologies that you can use to actually solve is what is listed here. Um, you Some of the connections may not even matter. I mean, you might think you just first draw a diagram, but you can, by experience, you know that some things will not matter. So eliminate those possibilities or use symmetry. So if the problem is symmetrical, try and simplify the problem and try to solve a simpler problem. So suppose it is a complicated flow in a pipe. Can you make the pipe straight? Okay, and then solve it as though you're solving it in a cylinder. So obviously if it's in a cylinder, you can assume there is a uh, symmetry in the theta direction, right, in the azimuthal direction. So something like that. Can you think of some symmetries, or can you come up with some physical model, hmm, which is a simplified form of the actual thing, and can you get it working? Sometimes when you work with physical model, your intuition to solve the mathematical problems becomes better. And sometimes other ways to strategize is to work backwards. So you know that I want to get to this unknown, and from there you come up with levels previous to that, and then try and get to the knowns. Very commonly in engineering problems, what you can solve is always a simpler problem. So what do you mean by a simpler problem? Mathematically, it means that you drop certain conditions. Some strict conditions are there, you drop it. Say you say that something was varying in space. Let's say the thermal conductivity varies in space, or the viscosity changes with flow rate. Drop that condition and say that viscosity is constant, thermal conductivity is constant, and so on. Or you simplify the geometry. As I said, look for symmetries and to simplify the geometry. And then restate the problem. Now, because you have got a simpler problem, restate it with some intermediate. So I'm not solving at the bigger problem, but I'm solving at a small problem. So it is important that all these things are actually done at the planning stage. So so basically what you're saying is that I'm specifying the methodology that I'm going to adopt to solve the problem. I've not actually solved it. The next step is actually to carry out the plan. So carrying out the plan also you can simplify. So things in the suppose you get a set of equations and you want to solve it in the computer. Now if you want to go to the computer directly to solve it, it might be very complicated. But before going to the most complex problem, you can solve for some simpler problems, which again you have to solve, but it's simpler. What we mean by simpler? In some things are varying in time. Okay, a transient thing, you don't solve the transient, but look for the ultimate steady state. What happens at the ultimate steady state? Or you can do what is called as a lumped parameter. Lumped parameter means it is system considered as a whole. Okay, you don't consider variations within the system. So suppose say something is entering at one temperature and exiting at another temperature. Obviously, let's say it's entering at 100 and exiting at 30 degrees centigrade. 100 is continuously changing and becoming 30. You are not interested in how and where 100 changes to 30, but you only look at 100 minus 30, which is 70. So you look at the lump, the entire system is considered as one box, a black box inside which something happens. So that's called as a lumping the parameter. You will learn more about this in modeling and simulation course later if you take them. Then comes next level of next higher complexity. You call what's called one dimensional model. So you, instead of saying lumping that the entire change is 70 degrees, it changes from 100 to um, 30 along a straight line, along a line, not in a three-dimensional way, but along a line. So that way you slowly make some simplifications and solve them, and look for analytical solutions. Once you have the simplified geometries or simplified equations, you can get analytical solutions. So that is what the first set of things that you will be solving. So once you are confident of this, then you can actually go and increase the complexities. Okay, increase the complexities and then validate against this simplest solutions. Finally is looking back. So what do we mean by looking back? So this essentially analyzing the results. So you have just solved them, but you don't know whether the results make sense. So the first thing that you need to do is present the results in a graphical way, often with errors of estimation and so on. So if we don't do many of these things, you don't know the conclusion that you're drawing from the results are right or wrong. So it's important that you present graphically at different axes and different, say, three-dimensional pictures and so on. So once you have the result, ask certain questions that does the number make practical sense? Okay, suppose you get some value of some parameter to be in kilometers, okay, whereas it has to be in meters. Obviously you've made some conversion mistake or solution mistake or so on. So some physical intuition of a sense of numbers will be helpful here. So ask a question and find out whether they make practical sense. Then are there, look at the plots, particularly look for some deviations. Are there any weird deviations? Normally you will expect things to go monotonously up or down, or there may be one peak or there may be two peaks. There won't be continuous ups and downs and something, unless that's really weird things that are going on. Mostly it is something that the numerical solution that you use to solve it to obtain the solution is not working. Okay, so these are the things that you first look for when you get a result. And finally, once you're confident, don't stop there. You also list down what worked and what didn't work. So this is what helps you later when you approach future problems, that what we call as intuition is exactly this. So you develop an intuition of what will work in future and what will not. Thank you.